Okay, let's get started. So everybody, welcome to our webinar. So my name is Greg Saraki. I'm part of the Habana Labs application engineering team. And I have with me Chen Levkovich from our product team and Pauline Etzelu from our marketing team. We're here today to talk about our Getting Started webinar series. And today we're going to focus on deep speed optimization and large models. Thank you all for being here. We're doing this on Zoom. So as we said, this will be recorded and will be made available for later viewing. We'll put the link to the event on our Habana developers page. If you have any questions, you can use the question and answer feature in Zoom. So if you go up here to Q&A in the Zoom bar, you'll be able to post questions and Chen, Pauline, or I will answer them. We'll have some time so we can try to answer those real time. And then we'll have time at the end to also have additional Q&A. So we'll have some time at the end. So please feel free to type questions as we go along. So the objectives of today are really to make sure that users are familiar with DeepSpeed and how it works on Habana. And I think the timing of this workshop is really, really great. You know, we see the explosion of these large models now with ChatGPT over the last few months, and now Bing from Microsoft and Bard from Google. You know, the use of these really large language models is exploding, and especially in the public domain. So it's really important that we all understand how these large models are optimized and how you get them to work, especially here on Gaudi. And we have some really good examples, and we'll run through one of them today. So we'll show the basic steps of what's needed to get DeepSpeed running, and we'll talk about DeepSpeed and why that's really important to manage these really large models. So we'll show the steps needed to get DeepSpeed running. One of the key things that part of DeepSpeed is the memory optimization techniques. That's ZeRO1 and ZeRO2, and how those and activation checkpointing can be used to reduce the memory usage and get these models to fit on the Gaudi processor. And we'll show you how you can use some of our APIs, our built-in APIs, to detect the peak memory of any model. So you can see where your model is consuming memory throughout the training process. And we'll have questions at the end. So we exit this webinar with the team being familiar with a couple of our examples, our tutorial, and show you how this works on Gaudi. So let's take a moment to remind ourselves what Gaudi is. So we have our first generation Gaudi, which we'll demo today, and we have Gaudi 2, our next generation Gaudi processor. And we remember that these are dedicated ASICs for accelerating deep learning. This is not a GPU. It's a dedicated ASIC processor designed from the ground up to accelerate deep learning. And so this is really designed specifically for that purpose. So we have the dedicated matrix multiplication and tensor processing cores for managing basic model training and inference. We have a dedicated software stack, so the Synapse AI software stack, which works with PyTorch and TensorFlow. And our Habana first gen Gaudi has 32 gigabytes of on-die memory, and our second generation Gaudi 2 has 96 gigabytes of on-die memory to really handle those larger and larger models. One of the key differentiators about Gaudi is also our on-package 10 100 gigabit Ethernet Rocky ports. So instead of having to rely on external networking with its extra cost and latency, we have on-die networking that on a chassis connects all Gaudi processors together directly, and also then can connect additional Gaudi processors between nodes or between chassis. So this is really this integrated NIC is really a differentiator in the market. So again, Gaudi and Gaudi 2, designed from the ground up for deep learning training and inference. So let's look at some of the use cases we're focused on today. Computer vision and obviously natural language processing. As I said at the beginning of the webinar, you know, it's really an exciting time to be part of this today. We see the explosion of these large language models that are really gaining the public's attention And so we are well positioned to be able to support these large models for both training and inference. So that natural language processing is one piece. Obviously, computer vision, one of the bulwarks of AI and deep learning. And then we also see multimodal. So, for instance, using stable diffusion, where you are typing in a text prompt and you get a picture back, or you're doing a search in text where you're asking to do a search for video and you get a response back in search in terms of a video or a picture. So these are really the types of domains where we're focusing on. And those can also apply to some of these vertical use cases. So you see that at the bottom, in retail, in manufacturing, in autonomous vehicles for computer vision, in fintech, healthcare, in chat. So all these use cases are really where we want to focus. So as we said, we look at the evolution of large models, we're on a path to 1 trillion parameters. And so these model sizes are on an exponential growth path. And this presents a problem because traditional smaller models from just a few years ago were able to the entire model would fit in a single device. So that made the training of the model fairly easy. You could simply split the large data set, but the model would be replicated in every single processor, which made it easy to manage how the model would get trained. But now the model's so big that the model doesn't have the ability to fit in that local system memory of the processor. And that causes some issues with latency, with compute time, and with just making sure that all of the model is trained and all the data is shared across the model. So we look at where we are today with GPT-3, with Bloom. We're already at 175 billion parameters, and we are well past that in academia today and going into the future. So advanced techniques are now needed to be able to not only split the data set, which is what we've all been doing for quite a while, but now splitting the model. And then not only that, splitting the model and maintaining now the memory and cohesion of all the data that happens when the model's being trained. So in traditional methods to do that natively in PyTorch or natively in TensorFlow is very, very challenging. And that requires a lot of modification and manipulation of the model. So from a user and data science perspective, that becomes very, very burdensome. And so one thing that's happened, we've seen, is the evolution of this new library called DeepSpeed. And so DeepSpeed has been created to be able to optimize these training parameters and optimize the distribution of how a model is trained across a large node or multi-processor node. So let's talk about DeepSpeed and what it does. So I'm sure many of you have heard about DeepSpeed. So let's talk about what it is. DeepSpeed is from Microsoft, and it is a deep learning optimization library that makes training easy for you as a user. And so this will take some of the details and difficult things around parallelization, mixed precision, data parallelism, and model parallelism, and manage those automatically. So as a user, it makes it much easier to modify your model only in a few steps that are required, and then let DeepSpeed handle all of the management of the data and how the model is then dispersed across all the nodes or all the processors that you're using. So let's take a look at the stack. So typically, you'll have your model here on top, and that model will integrate directly into PyTorch. And then that will work directly with your training infrastructure. In this case, this is the Synapse AI stack from Habana, and then run directly on the hardware. DeepSpeed here is basically in between your model and the framework. So instead of having to modify your model to handle all of that additional headroom or work to manage how to distribute this across PyTorch, DeepSpeed is doing that for you. And one of the key things that DeepSpeed does is optimizing system memory and how the workload is distributed across system memory. And so we'll introduce now the idea of the ZeRO algorithm. So again, the key takeaway here is DeepSpeed is not another model. DeepSpeed is not changing your model. DeepSpeed is just manipulating the data of your model to make sure it's more efficient and managed properly on your training network. So ZeRO. So ZeRO is an algorithm that is reducing the memory consumption used in each Habana processor, and helps partition the workloads across multiple Habana processors. And this is done by managing, in this case, the gradients and optimizer states. And the benefit here is integrating DeepSpeed and ZeRO requires no changes to your model. And we'll show that in the example in just a few moments. So we also look at activation checkpointing. So activation checkpointing is another way to further reduce how memory is being used. So as we look at a forward pass, you are having to calculate activations, which is the actual states of calculation as you go through the model. And in some cases, if you are managing all those activation states and keeping them in memory, you can make sure that you're running all those activation states in the memory. But if your model is large, having to keep every activation state of your entire model can require a huge amount of memory. So if you then are calculating those activations as you go through the model and only calculating them and holding them in memory as they're needed, then you have a significant reduction in memory size as well. And sometimes that can be at the expense of performance because you're having to recalculate your activations as you're going through the forward pass. However, that does have a significant reduction in memory. So let's take a look at a visual example of how the ZeRO optimizer works. So in this case, you will see that in a traditional distributed training example, you'll have multiple processors, and we'll typically split the data set across those processors. So that's your traditional data parallelism. So you're taking the large broad data set, splitting that into mini batches and separating those certain batches across certain processors. But your memory, your gradients, and your optimizer states are shared across all of the processors. What ZeRO will do is then separate and run a portion of the weights, the gradients, and the optimizer states across multiple HPUs, and then use techniques like all reduce and all gather, your traditional communication library techniques to then recombine everything and then recombine the model and continue the training process. But what you'll see here is that this can significantly reduce the amount of memory required. So then it allows that slice of the model to fit in the processor, in the Gaudi processor, and run properly. So let's look at what are some of the changes that are needed in a model to get DeepSpeed and ZeRO to work. So first, you have to install the DeepSpeed library. And in our case, Habana has a unique fork of DeepSpeed. So we have our own version of DeepSpeed on our GitHub page. So you can install, a user will be required to install Habana's version of DeepSpeed. And then in the model, today we support distributed data parallelism, or DDP, for all of the multi-card activity that we do. In this case, instead of using PyTorch DDP, you're handing that off to DeepSpeed. So the model is wrapped around DeepSpeed. So you, instead of wrapping it with the PyTorch DDP, you're wrapping it with DeepSpeed and using the DeepSpeed initialize command. And also, we then are changing the backward pass and optimizer to backward loss and model step. Again, these are details that are part of the DeepSpeed requirement. And you'll see a link down here for getting started that has more details on how to do that basic DeepSpeed migration. But these are the major things that are required to make that work. So let's talk a little bit more about those initialization functions for DeepSpeed. So there are two functions that are required. One is the DeepSpeed initialize, which we just talked about. So this takes all of your model, your optimizer, all your hyperparameters, and wraps them around DeepSpeed. And then the second function is DeepSpeed init distributed. So this, as we said, migrates you from the PyTorch distributed data parallelism and changes you into the DeepSpeed library. The most important part of this is making sure that we are changing the backend to HCL. And so HCL is Habana's communication library that we use that's based upon NVIDIA Nickel. So this is our version. It's the same API calls. It's our version of the communication library that handles the all gather, all reduce, and all those functions for distributed training. And we'll show both of these examples in our model in just a moment. So now that you have the modification of the changes for the model itself, now how do you make sure that you run the model in DeepSpeed? Let's talk about the model runtime. There are two files that are needed to successfully run a model using DeepSpeed. First is the DeepSpeed config JSON file. So DeepSpeed needs this JSON file that sets all of the configuration parameters for DeepSpeed execution. So you're setting the type of ZeRO optimization that you want to use, the specific runtime variables and configuration that you can set in DeepSpeed, the hyperparameter, the optimization technique you want to use. And so all of those things that are part of the DeepSpeed specification are defined here in dsconfig.json. And then to run the command itself, there is a run command, and we have that in basically a simple shell script that calls the model and points to this JSON file. And the most important part of this is we have a flag called use HPU. So in our runtime, we will show the use APU option, and that ensures that all of the model is then transitioned into the Habana accelerator. So we have several working models that you can run. So we have a very simple one click and run example on our model references GitHub. So we'll send everyone the links to this tutorial that we'll look at here in just a moment. And then we also have BERT 1.5 and 5B models. And we also now have our Bloom 175 model for inference using DeepSpeed is also available on our model references webpage. And then also we have worked very closely with Hugging Face. And so Hugging Face examples running on Habana Optimum, which is Hugging Face's library, have all been optimized and tested for DeepSpeed as well. So you have multiple examples here from the very simple. So if you're interested in just seeing it work, you can look at our PyTorch example on our GitHub page. You can look at this tutorial, or you can run some real world models from our model references or from Hugging Face. So from the beginner to the advanced, we have you covered. All right, so before we get into the demo, one more thing to show. Want to raise awareness here that we have an API. And part of our API here is showing the memory size on Gaudi. So we've included this API to detect the max memory usage, and you'll see these function calls, these 3 function calls here, that tell you the max memory, current memory, and of course reset. And so with some couple simple lines of code, you can implement this and see how much memory is being consumed as you're doing your run. And you can see this in all aspects of the pass. So you can see this during the forward pass, in calculating your gradients, and the backward pass. So you can see where in the flow the max memory is being reached. Okay, so let's get into it. So let's go now into the second part of today, which is our demo. And so we have a model called MinGPT, and this is a very simple configurable model to show the impact of ZeRO and activation checkpointing. This is a model that we found in the public domain, and is basically has all the details and structure. It's a 300-line model. It's very simple, but it is a GPT-based model, and all it does is, as I said, it's about 300 lines of code, and it inputs a simple sequence of numbers and predicts the next set of numbers. So it's not that complicated. We don't have to deal with a big data set to download. It's just feeds numbers into the transformer and then predicts the next sequence of numbers. But it shows us all the structure we need to understand how a DeepSpeed model works. So let's jump in and start working through this. So here we are. I'm on AWS today on the DL1 instance. So we have access to 8 Gaudis. So we'll run our HLSMI command, and you'll see here that we have access to 8 Gaudi processors. We're running our latest software stack, so 1.8.0. And right now they're all idle. And we look at our installed software, and you'll see here that I'm running in a Docker image, so we're using the Habana PyTorch Docker image. And you'll notice here that we already have our Habana PyTorch modules installed. And you'll see here we have Habana's DeepSpeed installed here. So as I said earlier, this is a Habana specific fork of DeepSpeed that has some Gaudi specific enhancements included. So this is our specific fork. So you'll see here we have DeepSpeed, Habana, PyTorch installed. Okay, now this model, this GPT model, is taken from our website. So you'll see here you can go to Gaudi tutorials, and under PyTorch and large model DeepSpeed, we have this model, and we'll talk through all the details of it now. So let's just get the model started. So we have our simple run script. So let's start that model right now, and then we'll start talking about the details of the model. Okay, so while that's running, we will take a look at our run script. Okay, so remember we talked about you need a run script to start to run the model. And this is it. So this is a very simple line here that's calling DeepSpeed. It's pointing to our demo DeepSpeed Python script. We're calling DeepSpeed, and we're pointing to the config.json file. And of course, we're passing it the use HPU command. So let's take a look at this initial DeepSpeed config.json file. So here we are in dsconfig.json. And you'll notice that this JSON file is giving you all the details you need to be able to run the model. In this case, the first section here is talking about our training batch size. We're using the Atom optimizer, and we're setting the learning rate and some other hyperparameters. And then in this case, we then can also set the level of ZeRO optimization we want to use. Now, in this case, we are, since this is a very simple configuration, we set the ZeRO optimization to 0, which means that none of the optimizations that ZeRO offers are being used in this case. So we're using DeepSpeed, but we're not using any of the ZeRO optimizations. So, and we'll see, let's all take a moment and know that based on the model we're using, let's predict what may happen here since we're not using ZeRO optimization. So this run script is now running in the background that we just looked at. So let's take a look at the model itself. So the model here itself, as I said, is about 300 lines of code and determines and defines basically the transformer and the transformer-based structure that is used in GPT models. And one thing that's really neat about this model is on line 142. And you'll notice here that you have the ability to pass in different sizes of a model. And so you have the ability here based upon the number of layers, attention heads, and embedding layers, you can determine the size of the model we want to use. So this model is very flexible. The structure is the same, but the size is something that we can make different. And so in this case, the size we're using today is GPT-2 XL. And so this is about a 1.5 billion parameter model. So quite a big model. And so we have the ability, and you can go into the run script and change the size of the model you want to run. So now that we ran this very simple config without using ZeRO optimization, let's see what happens. Now, as suspected, the model crashed. Why did the model crash? Because we ran out of memory. This model is too big. This model is too big to run without some of these optimizations. So what can we do? Well, let's look at some of our options. Instead of using a model without ZeRO optimization, let's run a script with the ZeRO1 optimizer and activation checkpointing. So I'm going to run this one instead. And let's remember here that as this is running, I'm going to scroll back up here. You'll notice here this is running running on all 8 Gaudis, 0 through 7. It's initializing the backend with DeepSpeed with our Heckle library, and it will then start to run. So we'll let that run, and off it goes. So now, instead of that, let's take a look at this new config. So now this is the config, the JSON config file for this new run. And you'll notice now that our ZeRO optimization is set to stage 1. So now we're using ZeRO1. And this is again is now managing how the optimizer states and gradients are managed and reducing the amount of memory being required on each of the 8 Gaudi processors. Also, we have activation checkpointing set. These default values are false at this time, but these are additional features that are default values in DeepSpeed. But the basic piece of activation checkpointing is active and it's in the code and it's working. So again, another way to reduce the amount of memory being used in each Gaudi processor. Okay, so let's take a look at our trainer script. So this trainer script here is used to basically do two things mainly. One is making sure that it's importing all of the Habana frameworks. So this is part of our general model migration. So one of the simple steps to make sure that your model runs on Gaudi is incorporating the Habana PyTorch. So our core and secondary APIs are included here. And then also we have here the memory usage. So we mentioned those APIs. So this is where we use the memory allocated and max memory allocated API calls. So if we are using the HPU, which we are, these are the simple functions here to calculate how to see those max memory allocations in the model. And at the end, we'll turn this on and see this actually in action and working. Okay. So now we see this JSON file working. You'll notice here in the actual run script that I kicked off a moment ago, you'll see now we are pointing to the new JSON file. We're obviously still using HPU, and we've passed in the activation checkpoint flag. So in all these cases, we are now using ZeRO1 and we're using activation checkpointing. And you'll notice here how fairly simple this is to really get DeepSpeed running. So let's take a look now at the model itself and the command to get the model up and running. So here in our demo, deepspeed.py, we'll start here at the top. We're obviously going to import all of the pieces we need here, including DeepSpeed. We're going to parse all our arguments. But here at the end on line 70 is where we have the DeepSpeed init distributed. So this is where we are passing in the Pickle backend and running on HPU. And then on line 149, in this case, this is where we can define the model config or model type. Now, in our case, I've modified our model to run the GPT-2 XL. When you pull this from our model garden, you'll see that it's running GPT Nano, so a very small model. And this will run without any of the DeepSpeed modifications. So if you want to see what we're doing here today, you can go in here and modify this to GPT-2 XL. Okay, and the other thing I wanted to show is our actual DeepSpeed initialization. So exactly. Okay, so let's go back to our model, and you'll see now that the model is completed. So now you'll see all 8 processes that were set. One process for each CPU was completed successfully. Now, in this case, again, this very simple model is doing a sort of a data set, looking at a sequence of numbers and outputting another sequence of numbers. So again, the model here is very, very simple, but it does prove that we are running DeepSpeed. And when we made this change from running without ZeRO to running with ZeRO, we now see that the model has successfully trained and successfully run. Okay, so one last thing we can try here is running the optional memory APIs. So let's look at in this case, we're going to just look at our shell script here, our DeepSpeed run command, and we will add a command called dump memory. And we'll run this again. Oh, it's not liking that command. All right, so let's debug this ourselves and make sure that we're doing this correctly. It is not dump underscore memory, it is dump dash memory. So let's make that fix. There we go. That's been fixed. And now, because we have passed in this dump memory flag, the runtime here will now start to calculate those memory values. And so you'll see as this begins to run, you will be able to see the details. Steve is asking the question, is there a reference manual that describes the structure of the tensors? Well, from the model, you can go and explore the model from our GitHub page. If you want to look at the structure of the tensors, we can dump this into our profiler, and you can use our profiler to see the tensors. Okay, so you'll see here then as we're going through these steps, you can see the memory here being reported out. So like in this case, before the forward pass, 2.8 gigabytes of memory. And the max here is, again, 2.8. So you can see the API starting to provide that information here in the model. So Steve, to answer a couple of your questions that you're asking here, let's go take a look back here at the results of this. So when we run this GPT model, we see the baseline here being 2.7 gigs. But when we use the ZeRO optimizer, we drop down to 1 gig. When we use ZeRO optimizer with activation checkpointing, it drops even further, which makes sense because those activations will be reduced. When we see this in the real world, running the same thing on our BERT 1.5b model, we see significant, because this is a much bigger model, we see a significant reduction in memory usage employing ZeRO1 and ZeRO2. So this is the data we see when running these on a little bit longer runs or on a real world model. So for all of you, how to be able to run this, there's two options. So to do exactly what I did today, you can go on to AWS and launch this on the DL1 instance and be able to run this. We also have the ability to run this on Gaudi 2. So on our Intel Developer Cloud, you can go to this link here, and this will get you access to the Gaudi 2 instance. And you can run this on either Gaudi or Gaudi 2. And you have the ability to run even larger models on Gaudi 2, because as we said earlier, Gaudi 1 has 32 gigabytes of on-die memory, and Gaudi 2 has 96. So significant improvement. So when you look at some of our collateral, let's take a moment to look at that. So our documentation, you can come right here into large models from our documentation page and come right here to DeepSpeed. And this will show you how to run our very, very simple example from our model references example folder. So you just follow all these steps and you'll be able to run a model. And this will take you into our user guide that talks about some of the other features that we have now enabled. We talked about ZeRO1 and ZeRO2 and activation checkpointing, and the ability to run not only that, but now even Megatron DeepSpeed is a new model that we've supported. So if you look at all of our models, we have on our GitHub page, after logging in and logging in, if you go to our model references page, you will see that we have our DeepSpeed BERT 1.5 and 5B model. And now we're also supporting the Megatron DeepSpeed GPT model that is called Bloom. This is a 13 billion parameter model that we run on Gaudi 2. So this is available. Additionally, we have, our Hugging Face Bloom model available for inference. And this is the full 176 billion parameter model using DeepSpeed for inference. And all the pieces we talked about today, setting up the config file, the DeepSpeed init, are all applied in these models. But the very simple examples here are, again, you can go to PyTorch, go to examples, and we have our simple CFAR example here, which is basically running this very simple model. Okay, so if we go back and look at our instance, again, we did get all the API completed and the model completed again. Okay, so I think we've got about 15 minutes left, so we will turn to some of the Q&A. Thank you, team, for answering some of the questions offline. Yeah, so Han is typing the answer to all the models. So everything you saw today is fully available. So again, today's model is available here under Gaudi tutorials, PyTorch, large model DeepSpeed. And I will actually put this in the chat for everyone. So everything that I did today, you can go and explore yourself. Everything here is available. So you have the ability to go do this on your own. Okay, question, does the Habana DeepSpeed fork support distributing a model on multiple nodes, not just processors belonging to the same node? Yes. So absolutely yes. And let me give you an example of that. So today in our model references, you look at our NLP model, and we have, let's see, excuse me, not BART. So in our DeepSpeed BERT model, let's show you our BERT 5B model. Here's an example down below that shows you how to run on multi-server. So the key thing here is just setting up the networking connection between the servers. But so all this is included here. And so we show you an example of running on 32 and on 128. So here is an example of how to run the BERT 5 billion model with ZeRO2 with bfloat 16 mixed position on 128 Gaudis. And so that those run commands are also here in these run scripts. So you can actually, if we go back to the top, excuse the scrolling, here is the run script. We should take a look at it. That shows you how to run on 128 cards. And you'll notice here that this is very similar to what we saw before. This is setting the run command. And then down here, it's just simply calling DeepSpeed. Now, this is a little bit more complex than the simple example that we had, but this is what a real world example looks like. But you can see all of the details are fairly similar. So we're calling DeepSpeed. We're pointing to the JSON file. We are running use HPU, and we're setting up the. Here is the JSON file, and here are some of the hyperparameters. So basically, everything we showed here in the demo today, you can see here in a larger scale. Okay. So for those on the call that would like to continue to ask questions, Steve, you have a few there that probably would be good. We can. I would point everybody to our forum. So forum.habana.ai is the one place where everyone can come for additional questions. You can come here to training and PyTorch and submit your questions, and those of us on the call and others on my team will respond and engage with you. Yes, so Gaudi 2 today for the general public is available in the Habana cloud. So that is the one place it is available today. So the easiest way for people to access Gaudi 2 is through the Intel Developer Cloud. That is correct. All right, so we'll stay online for a few more minutes. All right, everybody. So again, if anyone would like to, oh, and I'll do one more thing here before we go. So from our developer website, where you can get access to this is going to be here. So at developer.habana.ai, and you can come here to events and webinars. And this will be where we'll post the recording here. And again, back to our model references page. This will be the place where you can access this model that we've run through today. And so you can clone this down to your local repo and make all the changes and experiment with this model. All right, everybody. I appreciate everyone spending the time with us today, this hour, and hope you guys all got some useful information. As we end, you'll all see a simple 2-question survey come up. So if you please take the time and give us some feedback and answer the question, we'd really appreciate it. Okay, so everyone have a great day, and thanks for watching. Thank you.